Hello student to the physics of linear and nonlinear optical waveguide course. Today we have lecture number 32 and we will going to continue the modes in optical fiber. In the last class also we done few things and today we will do further calculation to find out the propagation constants etc. Well, in the last class if you remember we had a transcendental equation like this after putting a second boundary condition. And then we mentioned that if I able to solve this equation, then I can find out what is the value of this beta, which is important, which is basically the propagation constant of a given mode. So, in order to solve this transcendental equation, we need to simplify a bit, and that we can do with using certain relations using the Bessel functions, certain identities in the Bessel functions. So, these are called the recurrence relations, and few recurrence relations I can show here, using which you can simplify that. One is say 2 L by x j L x is equal to j L minus 1 x plus j L plus 1 x. This is one identity. Again I can have another identity. Also for modified Bessel functions I have the identity like this. From these identities, whatever the identity is written, so I can write it as this. If I simply from this 1 and if I use 1 and 2, then I can have this one. So, my j L x is simply L x j L x minus j L plus 1 x. This is say equation 1 I have. In a similar way I can have another equation. Please try it out and you will find that another equation one can also write in this way. So, from this 1 and 2 I can have, using this 1 and 2 I can write it as this. replacing x to u because my u is my variable here. That should be equal to this one. Why I am writing this? Because this equation already I derived in the last class, this one. I just replace this prime, which is the derivative, using equation 1 and 2 and put that, and I am getting this. Once I am getting this, I can simplify, I can have something like this. U L J L J L, this term will be 1, the first term. Here also we have the first term 1, so that will going to cancel out. So I will going to have something like this. This is my new modified transcendental equation, which, so this is a transcendental equation, and I modified this accordingly so that I can have, in the previous equation I have the prime, which is the derivative of the Bessel functions. So, I just remove this derivative by using the recursion relation, that is all. So, you please check this recursion relation and try to do this this exercise, and you will find a equation something like this. Now, like the previous case that we have done for planar waveguides, we are going to introduce this normalized parameter, normalized propagation constant B, which you remember is defined is this way. Mind it, the N effective is beta divided by k 0. So, this quantity beta square minus this my B is simply W square, because this part is W square divided by V square. What is V? By the way, the V is a V parameter, and V square I can write it as A square k 0 square N1 square minus N2 square, that is the value of V. So, if I now divide W square divided by V square, I am going to get this one. So, I just write my B in terms of W and V, so that I can use this B parameter in this equation. And what is U? Because in this equation you can see that the W and U is sitting. So, I am going to replace this in terms of B. So, one can find that U square plus W square is V square. Let me write it here. What was the U square once again? So, U square was A square k 0 square N1 square minus beta square, that was my u square, and my w square was a square beta square minus k 0 square n 2 square. So, now if I add these two things, you will going to find this v square. So, my u square is v square minus w square, and if I take v square common, it should be 1 minus w square divided by v square, which is v square into 1 minus b, because b already I calculated here as w square divided by v square. So, now I have everything in terms of v and b, and I know what is v, and b, inside the b we have the value of beta. So, I can write down my transcendental equation once again. So, my transcendental equation was u is equal to my transcendental equation was u j L plus 1 u divided by j L u is equal to w k L plus 1 u divided by k L u. That was the transcendental equation, and now I replace this u and w to b, and then u I replace as v 1 minus b whole to the power half j L plus 1, then I write v in the argument, it is 1 by b, then j L again I have v minus b equal to v root over of b, then k L plus 1, in the argument I should write v root over of b, because my w, so u is this quantity and my w from here it is v root over of b. And k L v root over of b. Please note that my v, my b is restricted with this limit, that is the most important thing. That is why we define the normalized propagation constant b. It is restricted to -1 to 0. So, that will make our life easier. By the way, one can also have another form. I should write this another form, because in some books this form is also been used. A similar looking form, only thing is that instead of having j plus 1, they have j minus 1. Using the recursion relation also, it is possible to find out that this transcendental equation is forming in this way. One can derive this equation using the using the recursion relation that was given earlier. Okay. So, after having these two equations, what basically we try to do? So, for a given value of L, there will be a finite number of solutions. And these solutions we write as mth solutions, such as m is equal to 1, 2, 3, 4 and so on. So, in this equation which is given here, either this one or this one, what I do that for a given value of L, that means I put a value of L and then I plot the left hand side and I also plot the right hand side, and this left hand side and right hand side, these two curves should cut at certain points, not only in single point, there is a possibility that they should cut in different points. So, these individual points for a given L is a single solution and we call it as a mth solution. If m 1, 2, 3, 4, I define the solutions as 1, 2, 3, 4 and so on. And these solutions are referred as the very important term LP LM modes. LP stands for linearly polarized and this LM gives the idea that which mode I am talking about. So, LP, this subscript is important, LM. So, L we know that it can be 1, 0, 1, 2, 3 etc., and it is a number of solutions. If I am dealing with first solution, then it should be m equal to 1. If I have a second solution, this should be 2. If I have another solution, it will be 3 and so on. So, we will going to see that how this basically looks like. So, let us do one example. So, for suppose for L equal to 0, what happened? I have the transcendental equation V 1 minus B whole to the power half J 1 V 1 minus B divided by J 0 V 1 minus B. This is my left hand side of the transcendental equation, and the right hand side I have V root over of B K 1 V root B divided by K 0 V root B. Now, what I do, I will change, V is a variable. So, the variable is here, variable is B. So, B will going to change every time and I will try to find out what is the solution. If I now plot these two solutions, left hand side will go like this. By the way, this is B, so it should be restricted to 0 and say 1. This is 1 and this is 0. The right hand side will show something like this. And I will have a cutting point here sum. So, this is for L equal to 0 and I am having a value solution B which is nearly equal to 0.41616. This is L equal to 0. So, I should have LP 0 and this is the first solution. So, this is the mth solution. So, m is 1 here. So, this is m equal to 1. So, this is LP1 solution and for which value I need to put the value of the B as well, because B is a parameter that need to be defined. So, this is for V equal to 2. So, for V equal to 2, so what we do, I put V equal to 2 in this equation and then I vary my B to 0 to 1, and when I vary my value B 0 to 1, I can plot the left hand side, but everything is known. This is a Bessel function of first kind with 1 and this is Bessel function 0 j0 j1. So, you can use the computer to plot this portion and also in the right hand portion for a given value of V, which is 2. When you do, you will find that these two solutions is like that, these two functions is changing with respect to B like that, and there is a cutting point here somewhere. So, this is the only cutting point where single cutting point, and this cutting point is around B nearly equal to say 0.41616, and this is a cutting point for L equal to 0 and m equal to 1. Why m equal to 1? Because we are having the only one cutting point. So, that is why it defined as m equal to 1. If I have another cutting point, we should write m equal to 2 and so on, and this is basically corresponds to LP1, LP0. Now, for this same V value, if I plot for same V value, if I plot this equation for L equal to 1, initially it is for L equal to 0, now I am plotting for L equal to 1. I am going to have two function like this. This side I am plotting B, which is 0, which is restricted up to 1, and this is 1. And when I plot, there is no cutting point at all. So, that means, so the conclusion is no point of intersection so that means there is no guided mode corresponding to L equal to 1. So, for L equal to 1, there is no guided mode because there is no solution at all for beta. I can do also for higher value of V, then it is interesting. So, let us put say for V equal to 6.5 and try to find out L equal to 0. That means so L equal to 0 and so this is B. So, 0 to this point is 1, this is B, and if I plot this transcendental equation, I will have the right hand side as curve as this one, but something like this for sorry, the dotted line is seems to be the left hand side, right hand side, and the left hand side, sorry, left hand side, correct, and seems to be something like this. These are the, so here interestingly one can find that I am having two solutions, here one and here another. So this solution I can write it is for m equal to 1 and this is for m equal to 2, and this is for L equal to 0 I am plotting that. So that means this is for LP 0 1 and this solution can term as LP 0 2. These are the two solutions I have. Sorry, this, okay, I have a mistake here. Okay, you have to be careful. So I can't put m equal to 1 here and m equal to t2 here. This is wrong because the first solution, so this is m equal to, so very important thing, this is m equal to 1 and this is m equal to 2, this is LP 0 1 and LP 0 2. Why? Because for this value I have the highest b. So this is say let me write, this is the solution beta 1 and for this the solution is beta 2 which corresponds to B1 and B2. So B1 is greater than B2. So B1 corresponds to m equal to 1 solution, the first solution, and B2 corresponds to m equal to the second solution. The highest value of B always corresponds to the first solution, which is related to the fundamental mode. Well, I can extend this for L equal to 1. If I do so, say V equal to 6.5 and you can see the value of V is much greater than 2.40, this cutoff. So, we are going to expect more than one mode to be supported by the fiber and L equal to 1 and eventually I am getting this. When the value of V is higher, I am expecting more and more modes, and already here we find two solutions. And now if I go to higher value of L, then I can excite more higher order modes. This is so I can have the right hand side like this is changing like this. This is 0 up to this, it is say 1. This is along this direction I am plotting B, and I have two solutions like here and here, and these two solutions corresponds to, again this is for higher values. So, this is my m equal to 1 solution and this is equal to m equal to, this is second solution. This solution corresponds to LP 1 mode, this solution corresponds to LP 1 2 mode. After having all this, so for if I change my value of B, I am going to get the cutting points for a given value of V. So, I can have the value of B. So, I can plot that like we have done in the previous case. We can plot this. This is again a well known plot. So, 0, this is 1, along this direction I plot B as a function of V, and I am going to have this kind of curves. So, along this direction I am plotting V, increasing V. The first case I am gathering all the solutions for say 0 1. So, L equal to 0 and M equal to 1, these solutions I will take for all the values for different V's. In the second case, I can have the solution like this 1 1. Third case, suppose I am having the solution like 0 2 and so on. So, I should have different this kind of curves which basically gives the solutions, different solutions of different values of L and M. In the first branch I am having for L equal to 0 and M equal to 1 solution for all different values of V. This value is around 2.4048 if I calculate for step index fiber. So, this is a very meaningful thing. Note for V in between these values, we have only one mode, and this mode is LP01 mode. So, when V value is less than 2.4048, we call this fiber a special name called single mode fiber. Why it is that? Because if I look carefully, that if the value of V is less than 2.4048, there is only one mode present and this mode is LP01, no other modes is there. However, if I increase the value of V, you can readily find that if I have some point here which is greater than that value, I may have this solution here one and here also. So, not only LP01, I can have a solution corresponds to LP11 also. So, I have, instead of having one mode, I am having two mode, because the value of V here is greater than this value. If I write V0, so it is greater than V0. So, V0 is a cutoff value for which I am only having one fundamental mode. This is called the fundamental mode, and if I increase the value of V, I am basically getting more and more number of modes. When I am having only one mode for a fiber, then this fiber is called the single mode fiber, which is a very important component, especially for the communication. Normally, we like to have a fiber which can only support one mode. With this note, I like to conclude my class here. In the next class, we will learn more about mode and how the mode is distributed over the fiber. We try to understand with proper mathematical descriptions. Thank you for your attention. See you in the next class.